Hello everyone, welcome back. Today we'll talk about some definitions and nomenclature. So first we try to understand these terms with respect to one example, our own Paralympian in archery, Ms. Sital Devi.
She is an amazing archer, Sheetal Devi. At such a young age, only 17 years old, silver medalist at last year's World Championships at the age of 16. Oh, what a start for Devi.
17.
So what we see here that she can hit the bullseye in the first go itself, and it happens because of a lot of practice. But at the same time, the bow they have many settings here, and based on the environment there on that day, the wind conditions, they can change those parameters, they can set it, and because of the consistency, the practice they have, they can control all the variables precisely, and as a result, she can hit the bullseye with the first arrow itself. And on any given day, this is what we can see, and yeah, we can say it's a very precise, very accurate. So we'll be talking about these two terms, accuracy and precision. So let's try to understand it through this dart game. So if we talk about this first case, when we try to hit the bullseye and throw the dart, what we can say is there is no consistency, it's going everywhere. Now talk about the second example here. Although it's going to one corner, but then all the darts are going to the same location, more or less to the same locations. In third one, they are closer to the bullseye, but little spread. And in the fourth one, what we observe that yes, they are all going to the center, hitting the bullseye. So we are introducing these two terms now, accuracy and precision. In the first one, what we can say is both are low, it's everywhere, and very difficult to bring it back to the center. And yes, what we can say with respect to the sports, yes, one needs to put a lot of effort and yes, practice. But in terms of machining also, in products, in instruments, if we have to achieve higher accuracy and higher precision, it is very difficult because everything is very random, and the random noise, the random things happening in machine can't lead to very accurate or precision machines. In the second case, what we see here, although we have low accuracy, it's far from the center, but what we observe, what we are saying here, it has a high precision. So there is a likelihood that with some adjustment, the person whoever is throwing the darts, he can readjust his positioning and may be able to hit all the darts to the center. So it's possible to achieve high precision in this case, and with some adjustment we can also achieve high accuracy. In the third case, what we are saying, high accuracy, so it's close to the center, all the darts are there nearby, but not very precise because still there is a randomness is around, and again getting a very accurate system going to the center is a difficult. Of course, the last case, this is what is desired in many cases. We want to have high accuracy and high precision at the same time. So, let us take the third case where although it's off, so what we see here, all the darts are away from the center. So, it's off, so there is low accuracy. So, it's far away from the target point. So, the accuracy is low. But what we also observe that all the darts are going to the same location. So, it means there is a systematic error, what we can say. There is some offset or some adjustment is required. So, if we provide that offset, then we can achieve both high accuracy and high precision. And what is required is compensation and proper adjustment. So, many times we are looking at these cases where the precision is high, even though the accuracy is low, but with the high precision, with the proper adjustment and compensation, we can achieve high accuracy. So, we will be talking about these three terms: accuracy, repeatability and resolution, and try to understand more and through the example. So, if we look at the definitions, so what we say accuracy of an operation. So, here we are talking about two things: actual value and target value. So, this is the target we have, and these are the actual values. So, what we are saying accuracy, when we talk about, we say closeness of the agreement between the actual value resulting from an operation and the target value of the quantity. So, how far or how close the operation is from the targeted value. Now, talking about repeatability, we talk about repeatability of result of operations. So, it is a statistical parameter, and what we are saying is talking about successive operations and of the same quantity. So, when we are doing the same operation under the similar conditions many times, so in the successive operation, so closeness of the agreement between the results of successive operation, which is here, of the same quantity carried out under the same conditions. So, we wanted to hit the target here, wanted to go close, but every time we make the movement, do the operation, is going there. So, those are the actual values, and that is the repeatability. So, we try to go once again. So, this is the target we have, and suppose if you are doing the operations successively, so they are clustered around. So, we can say it has a very good repeatability, or previously we said high precision. So, this is what we call accuracy. So, the cluster and how far is away from the target point, that is called accuracy. But when we zoom in and try to see the operations, the different events, what we realize, they are clustered around, and the radius of that circle, that is called repeatability. So, I think it is very important to understand these two parameters, the repeatability and accuracy. And what we also understand, that accuracy we can always compensate, but the repeatability is very important, and if the repeatability is large, we cannot make a very accurate systems. So that's why in this course we'll focus on repeatability part and how to achieve that. The other term what we will be using frequently is the resolution. So resolution is always of the measuring devices of the sensor, and what we say is the smallest difference between indication of displaying device that can be meaningfully distinguished. So whether it's electronic or analog devices. So we have a vernier, we have a micrometer, we know how to use them, and what is the smallest measurement we can do, that is the resolution. So moving on, this is the famous chart about precision machining, and presented by Taniguchi in 1983, and he talks about trends in precision machining. What is important to understand here is when you talk about normal machining, this is the trend. So this is the year line, and what we see here is achievable machining accuracy. So if you see the timeline, this is 1980 and this is 2000, and probably now we are somewhere here, 2025, right? What we see even for in 1980s for normal machining is more or less 5 micron, but by the time 2000, it has reached 1 micron already. And if we go in the same way, what we realize that in now in 2025 we are talking about even the normal machining, the kind of achievable machining accuracy we are talking about is of the order of 0.1 micron. So something which was 5 micron in 1980 with the normal machining, now it's 0.1 micron. Now when we say precision machining, this was 0.05 micron in 1980s. In 2000, it's 0.01 micron. Now you can think of where it's coming. So very high, going towards nanometer. So sub-micron level we are already talking about when we are talking about precision machining. When we talk about ultra precision machining, where we are? In 1980, we were here, 0.005 micron. In 2000, this was 0.001 micron, and we are already hitting the 0.3 nanometer atomic lattice distance, right? So what we realize that even in the machining, moving from normal machining to precision to ultra precision machining, we are going to more or less to nanometer levels, and it's very important to understand how to achieve these numbers. So we are talking about repeatability of that order. So we can talk about the different kind of machine tools, we can talk about different kind of measuring instruments, and it was presented by Taniguchi way back in 1983. So what we understand that what is the driver, why we are talking about precision machines, or more or less we should now start saying ultra precision machines. So one of the key driver is the machine tools itself, the kind of numbers we are talking about, submicrons kind of repeatability, or nanometer kind of repeatability if we are talking about the milling, grinding, turning operations. We have precision diamond turning machines for creating different kind of surfaces to create precision parts. We also need to do measurements for the characterization, for the to know how precise the components are, right? So we have these coordinate measuring machines, different kind of microscopes for the measurement, and there we are talking about some micron, 0.01 micron, or even nanometer kind of repeatability we are talking about. Then comes the semiconductor systems, the lithography equipments. We are talking about lithography equipment also. So wafer steppers, nano imprinters. So we would like to design and make chips of that order, and how precisely they have to be moved, the overlay, the step size, they are very precise, and therefore it's very important to understand how to achieve those numbers with these machines, how to make these processes so that we can create parts of that precision level, how to make these instruments so that they can measure things, even the biological things or the defects at microscopic level. And so we need to do measurements at the atomic scale. And the applications, the real driver is the market, the growing market of the consumer products. So the computers, the computational facilities, workstations, data centers, data servers, we want to do a lot of artificial intelligence, machine learning, so cloud computing, how to facilitate those kind of activities, how to create that facility, how to make them run. Second is the mobile devices. These days we have, so the features are cramped. We want to do everything with our mobile devices, with our phones, with the tablets. So the chip sizes are decreasing, the microprocessors, all the electronics getting smaller and smaller, and they are getting a very small footprint in our devices. So how to make those things precisely and to create each and every feature in that small real estate what we have. The electronics, the home appliances we use, they are also becoming smarter. There is a concept of a smart homes already. We want to build things which can sense, which can act on its own, the fire safety, the safety of the elderly people. So everything requires a lot of computation, a lot of electronics, and this will be achieved only if we are able to achieve precision systems, and if we are able to design and make this system our own. Robotics is also slowly getting ubiquitous. It's everywhere. It's for entertainment. It's for taking care of the elderly. It's even in the medical devices, medical robotics, rehabilitation. So all these things are like part of our life, and we want to use these systems very efficiently, and at the same time the focus is and focus should be to get these things here. We should be able to design, develop and manufacture here in India, and then only we can get the best use of these technologies. So what we understand that what is important, if we really want to build these systems, we want to have deterministic behavior. So if we want to achieve high precision or call it ultra precision, we want that there should not be any randomness. So very well said. Random behavior leads to random results. So we want to control that. We want to reduce the randomness in the system. So how to bring determinism in our design? And the key aspect of that is kinematic design, and which is also called exact constraint design, which we'll be covering in detail in this course. And if there is any offset or any adjustment required, which will be later of the order of micron, can be easily adjusted using compliant mechanism with the flexures. And one of the problem in many of these devices or in many of these designs is friction. So how to get rid of that friction? So we'll be using compliant mechanisms, and we'll talk about different kind of flexure design, compliant mechanisms designs in this course one by one. Thank you.